asked.
You did it. Okay.
Yeah.
You are perfect in the organization, as always.
Don't worry. So let's start. So welcome everybody to this new session of the Simna Seminar course. This week has been a bit busy because we had a coffee talk, a seminar yesterday, and today another one. But thank you very much, everybody, for coming today to this seminar. Today we're pleased to have with us Ivan Markovsky, who is an associate professor at the department ELEC of the Free University of Brussels. Ivan has recently applied to an ICREA senior position at SIMNE in the Credible Data-Driven Models group, and his main research interests are computational methods for system theory, identification, and data-driven control in the behavioral setting. Ivan, when you want, you can start.
Okay, thank you for the introduction. It's a pleasure to introduce my research topic. As Pedro asked me, I'll give first a general overview. So this is the core research topic I work on, structured low-rank approximation. And instead of zooming on some particular computational methods, which can be further on discussion with you, I decided to show one case study, which is from metrology, the problem of dynamic measurements, and it's illustrating some of the techniques I'm using. So the first part is the general overview, the second and the third are the application. I would invite everyone who has question or doesn't understand something to ask the question immediately instead of waiting. That may be useful in general also for me to calibrate the presentation and the level. So the problem of structured low-rank approximation is a general technique in numerical linear algebra, and it's very simple to state. We're given a matrix, and we want to approximate this matrix with a matrix of reduced rank. Typically, as a hyperparameter, I'll assume that the rank of the reduced matrix is given a priori. It can be also estimated, but that's another topic that I will not cover in this presentation. What is special in this problem is the structured keyword. So this is imposing some additional constraints on the problem. If we have unstructured approximation in Frobenius norm or the spectral norm, the solution is given by the singular value decomposition, which many of you know. But the problem is much more difficult if you have additional constraints, which require some typically non-convex optimization techniques. So this problem appears in a number of fields. The first one is where I mostly work in, systems and control. And two representative problems of this field are model identification and model reduction. What is the difference? In model identification, we start from observed data. And in model reduction, we start from a given model. It can be complicated large-scale model of a process that we want to simplify for either computational purposes or some other goals that we have in mind. For example, if we use it for control, we cannot use the original complex model, but we can use a simplified model. Another field of large field of applications is signal processing, and one particular problem of interest is image deburring. Here we go from one dimension, which is the systems and control field. We have one independent variable time. In image deburring, we have two variables because it's spatial. And more generally, you can have multidimensional processes. They also can be covered with some more complicated structures in the same framework. Yet another area of applications is in computer algebra. I worked in particular on the problem of approximate common divisor, which is a theoretical problem, but also it has some interesting applications. And finally, a huge area of applications is machine learning. It goes with the generic name of dimensionality reduction. So here we have a spectrum of large-scale, nonlinear, all kinds of complications of the original low-rank approximation problem. So what allows us to fit all this variety of application areas into one common denominator, which is the structured low-rank approximation problem? It's the structure. In every one of these applications, you see different type of structure. So just to give you an idea, in systems and control, typical structures that appear, and that's something that you'll see in the presentation, is what's called Hankel and Toeplitz structures. In two-dimensional and higher dimensional, this will be more complicated because it will be block Hankel-Toeplitz, where each block itself is Hankel-Toeplitz. It's nested. In computer algebra, for the problem of approximate common divisor computation, the structure is Sylvester. So the Sylvester matrix is rank deficient if and only if the polynomials which parameterize it have common factor. And that's a way to compute common divisors and do it also approximately. In machine learning, the diversity is even larger because they use what are called the feature maps or kernel tricks. And these are mapping the data to higher dimensions with some nonlinear transformation. And this nonlinear transformation is the type of structure that gets in the picture as well, like polynomials or all kinds of different feature maps. So this has to do with mostly modeling, but more recently I got very interested, and now this is also very active research topic in not modeling, but bypassing modeling. So this is the red path going from some observations to some final decision, which can be different in different problems. But let's say in control, we want to find the control action that achieves certain behavior. In forecasting, we want to predict the future of our process. And to get to this final information from the original observations, we have to typically first get a model. And this is the system model identification step. And then using the model, find the desired control action or future prediction. Now, what we can do as an alternative, and it's initially just a curiosity-driven question, is do we need the model? Can we bypass the model by going directly from observations to prediction? And this is more in the spirit of machine learning techniques, which are actually black box, and they directly give you the what you're interested to obtain without seeing the special structure behind the data generating system, without getting explicit parametric model. And this direct path has advantages. It's also a very new and young area of research in the field of systems and control. It relates, and the techniques which are used for finding this direct path are namely the low-rank approximation methods with the structure on top of them, and with a new feature, which is something that I didn't mention in the previous slide. We also have missing data, and this comes with the keyword of completion, matrix completion. To give you one specific, although toy problem, consider we have one-dimensional time series. So just observations of a variable y, and the past data which we are given goes up to some current moment of time t. The goal is to do forecasting, to predict what will be the future values of y. These are the values in red. If we do the following transformation of the data, we put it in a matrix, that's the Hankel matrix, which contains in the upper triangular part the given data, and in the lower triangular part the missing data, what we want to forecast. We can solve the problem of forecasting as a matrix completion problem because we have another property that this matrix, when it's complete, must be of reduced rank. And this completion will give us what we need for the future prediction. Under what conditions this completion is unique is a theoretical question that is very important, and this is the basis of the theory behind these direct data-driven techniques. So why we do this transformation to Hankel matrix? Why we put the data in this specific form? The reason is this theorem that states if our time series, that's an assumption I didn't say before, is of the special form of sum of damped exponentials, and namely we have n exponentials. Then reshaping the data in the matrix shown here, where the number of rows of this matrix is one more than the number of exponents n, namely n plus 1, and the number of columns is depends on the number of data samples, but it's typically many more columns than rows. Then the matrix is of rank n, therefore it's rank deficient. And this thing is directly related to having a model behind the data. So this model, as I stated, is sum of damped exponentials. So the signal y is a weighted sum of exponential functions. And the parameters of this model are the frequencies of these exponentials, they're complex exponentials. Another way to represent the same signal, and that makes links to physics and applications, is to observe that, again, we have a theorem. This sum of damped exponential signal is satisfying difference equation. So we have constant coefficient ordinary difference equation that holds true for all the data. The notation here is sigma is acting on a signal to shift it, so sigma of y at time t as yt plus 1. And if we apply a finite number of shifts, namely n, which is the number of exponents, is giving us a formula which is homogeneous constant coefficient difference equation. One more, here the parameters are the p's. One more representation of the same model is a state space representation, which is very popular in control theory, where the output of the system, or the signal that we observe y, is a linear function of another variable x, the state. And x satisfies a first order vector difference equation. So there is parameter a, now a matrix, and parameter c, which describe the same sum of damped exponentials process. There are many relations now between the parameters. For example, the eigenvalues of a are the roots of the polynomial defined by the p's, and there are also the z's that appear in the sum of damped exponential. So this is the framework we were working in, and this is what is the setting in systems and control that we call a model, this sort of signal which satisfies, for example, the state space equation, which is linear constant coefficient, and that's why the model class is linear time invariant. The n, which appeared in all the representations, is a measure of complexity of the model. Typically, we want small n, but of course, it gives us less freedom to fit the data. So it's a trade-off parameter between complexity and accuracy in data fitting. And I'll denote the class of all models of the sort that I described, linear time invariant, of maximum order n with this calligraphy L sub n. So this is a set of models. And now the modeling problem can be stated as follows. If we're given data y, observations, we want to approximate this data in some norm with a trajectory y hat, which is by construction guaranteed to be sum of damped exponentials with at most n exponents. Namely, y hat belongs to a model b hat, which belongs to the class of models that we are interested in, L sub n. And as I showed a few slides back, we have this equivalence that if we have such a signal, which is sum of damped exponentials with n exponents, equivalently, we can write this constraint, y is an exact trajectory, in the form of a rank of the Hankel matrix constructed from y with n plus 1 rows is equal to n. And that allows us to rephrase now the identification problem into computational problem, which is low rank approximation with the structure that the matrix that we approximate is Hankel. So you see here the connection between system identification, the problem on the top, and low rank structure to low rank approximation, the problem at the bottom. So far, we have done nothing but rephrase one problem into another. Still, the big question is how we solve the problem. And that's where I don't want to go into the details because there is a whole variety of different techniques. The bad news is that this is a non-convex optimization problem. So we generally need some local optimization techniques. There are specialized techniques that are suitable for this class of applications. Therefore, they're more efficient and robust. I'm working on this, and there is a software package related to these methods, but I'm not going to present them here. Other techniques which are interesting, when we use local optimization, we always need initial approximation. And as you know, when the problem is difficult and we have many local minima, the initial approximation is extremely important. So how we get this initial approximation? That's the question that we ask when we derive alternative methods which are suboptimal, but they give some, in some way, good approximation. One approach is convex relaxations. We replace the non-convex problem with some convex problem that we can solve uniquely. And this solution of the convex problem gives us the initial approximation for further optimization. And another class of techniques which is used in system identification is what is called subspace methods. So I'm going in the second and third part of the presentation illustrate the use of subspace techniques for a specific application. Maybe here I pause for any questions if you have anything at this stage.
Yes, Ivan, one question, because you mentioned that at the end, in this identification or optimization, at the end you have to provide or to compute the number, the values of a certain number of parameters. What is the actual typical dimension of the problem you have in mind? So how many free parameters to identify? So how many, what is the dimension of the design space in the cases you typically deal with?
Okay, yeah, that's a very good question, because indeed, when I'm talking about specific optimization techniques, they'll be tailored also to precisely this point. What are the dimensions? In typical applications in systems and control, we have very large dimension of the variable y. It can be large in both number of variables, because it's vector time series, as well as number of samples. So this is something that would be taken care of by efficient approximation of the y with y hat given the model. This is typically the common filter step that is linear in computational complexity in the number of samples. Now, your question is rather on what is the size of the model. This has to do with the n, the rank. And here things become much more difficult, because if we have to consider large dimensional model in the sense of high rank, then we have to deal with large dimensional matrix in the approximation problem, and also large dimensional parameter vector of the model, which makes the problem in high dimensional space as a non-convex optimization. And here, the dimensions are not more than, let's say, a few hundreds. So although y can be of the order of hundreds of thousands, the size of n, I would say, is not more than a few hundreds. And even this is considered to be rather high for applications in control. In control, typically n would be tens, not hundreds. This imbalance between size of data and parameter number of parameters is very important, because it allows us to make efficient, design-efficient methods that are basically eliminating the variable y hat. So in this optimization problem, first we need to parameterize the rank constraint, typically with basis for the kernel. So this gives us two sorts of variables. One is y hat, the other one is the kernel parameters. And one is very large, y hat is large, the kernel parameter is small. And then we can, with fixed kernel parameter, namely fixed model, make efficient computation of the cost function and the gradient. And that means we have to be only optimizing over the small dimensional vector in the nonlinear space.
Thank you very much, Ivan. Already tenths of parameters is not bad. I mean, in our applications, we are also very much limited with the number of, say, the parametric dimensions.
Yeah, let me add, because it's a long answer to your question, but it's a very important question. And let me add that it's not really computational issues of efficiency that stop us go to large dimension, but rather the fact that we are not getting meaningful model in very large dimensions, not at least with optimization, Ochoa optimization techniques, because the search space is just too large to be able to even approximate well the original model. So then reduction of the model, and that means small n, is more interesting.
Thank you.
If there are no additional questions, I'll proceed with the application. So this is something that started with question, actually problem in a textbook. And the problem I'll read for you is a thermometer reads 21 degrees Celsius, which has been inside the house for a long time. And this thermometer is taken outside. After 1 minute, the thermometer reads 15 degrees Celsius. After 2 minutes, it reads 11 degrees Celsius. What is the outside temperature? What is added in the problem is additional information that the behavior of the temperature is governed by the Newton's law of cooling, which is a first-order differential equation. And this suggests a very interesting idea. So if we take a few samples of a dynamical process, from these two samples, we can predict the steady state value of the process, which is the thing of interest here to measure the temperature, without waiting for the transient to die out, because this transient may take much longer time. And the textbook problem is very academic. It's about first-order dynamics because of the Newton's law. It's about exact data, in which case turns out we need only 3 samples of the process, and we can do the prediction by just some computations, which are analytical derivation of the answer. What intrigued me in this problem is that we can make a generalization of it to higher dimensional processes, which means something a lot more complicated than exponential. And we can go, in this case, to noisy measurements, therefore measure more than 3, the minimum necessary number of samples, and do the computation recursive in time in order to update the answer so that we not only get faster the final steady state value, but we also get it more accurate by averaging the noise. And if we implement this solution in practice, I expected it will be something important in general for metrology, because it's a generic tool for speeding up any type of sensor, which has some complicated dynamics, which we probably don't know in advance. It's also a direct application of signal processing techniques that I was working on, so that's what I'll present. So here is the more details about the simple setup in the textbook. So we have some heat transfer process between the environment and the thermometer. And this heat transfer process can be explained as this first-order differential equation. It has a single parameter, which is a positive constant. Because of the fact that we don't know the environment in which we measure, we actually don't know this constant A, which means that in practice, we don't have knowledge of the process that governs the dynamics of the measurements. And that means we have to do it adaptive. We not only estimate the value of interest Y, but also the model. And doing this in a classical framework would be the model-based approach. We first identify the model, and then we use the model for filtering. But using the direct techniques of data-driven, we can avoid the modeling of the process, namely getting the parameter A. We can directly predict the steady state value, and that's something new that I'll show you. Slightly more complicated process is the dynamics of a scale. So we measure a mass capital M, we put it on a platform with mass small m, and we can model the measurement process as a second-order mass spring damper system, which is now second-order differential equation. Note that the unknown parameter m that we want to measure enters into the equation, therefore it affects the dynamics. So here are simulations with 3 different values of mass, m1, m5, m10. You can see that the heavier the object we measure, the more transient the process is, therefore we have to wait longer if we rely on a steady state measured directly from the scale. But doing some predictive processing, we can get the exact steady state value, which is the dashed line, from a finite number of samples, provided they're noise-free. So what will be the general setup assumptions? We have some measurement process. We don't know what it is, but we assume that this is linear process, like the differential equations that I just showed you, they're linear constant coefficient. Second assumption is that the value that we measure is constant in time. I'll relax this later on, but for the moment, let's say the value that we measure doesn't change while we do the measurements. And final assumption is a very reasonable one. It's called calibration of the sensor. We assume we know the DC gain so that we can say what U is, the input variable, given Y in a steady state regime. So what would be the model-based approach and what would be different if we do data-driven methods? First, a little bit more details of the measurement process. We assume that we have, of course, noise. In practice, that will be always the case. So we have true value of the measurement process Y plus measurement noise E, which this is fourth assumption. I will assume it's zero mean, white, and Gaussian. And the true value consists of the steady state value U bar plus a transient process U0. And the U0 satisfies linear time-invariant dynamical system of order n. Therefore, we can represent it in one of the 3 ways I showed earlier, in particular in a state space form. So we have here the parameters A and C that appear in the state space representation. And then we can write explicit system of equations. We discretize the process in time. So we measure the output Y at time discrete time 1, 2, up to some capital T. And we can, unfolding this difference equation, write out what is YD at different moments of time, and you'll get this system of equations. So we have the constant plus the transient plus the noise. And the transient is governed by the dynamics of the system described by the parameters C and A. So if we have the model given, therefore we have C and A, we have everything, let me go back, everything about this matrix, which I call capital O. And therefore we can write a system of linear equations for the parameters of interest, the steady state value, and another nuisance parameter, which is the initial conditions of the dynamical system. Estimating these parameters from the data means we have to solve approximately system of linear equations, one of the basic problems, doing it in a least square sense, and that's justifiable because we have assumption of zero mean white Gaussian noise. Therefore, this will be even maximum likelihood estimator. We get the problem at the bottom, and this problem can be solved recursively due to the special structure of the capital O matrix. So by measuring new data points, we can update the solution. And this is the celebrated Kalman filter. So we have a readily available solution for the problem of dynamic measurement, provided we have given model. What will be now the solution if we don't have the given model, which is what I argued is the real situation? We can first identify the model, and then using the model, apply the Kalman filter. This is the model-based approach. But we can do another thing, which is a data-driven approach. And it's based on a simple observation. Because time is going up, I'll quickly show you the main idea. if we construct the Hankio matrix of the difference data, the image of this Hankio matrix is exactly equal to the image of the matrix O that appeared earlier and depends on the model parameters. So using this fact, we can, in the system of equations that we solve with the given model, replace capital O with the Hankio matrix of the data and solve this new system of equations, which depends only on the data, to get the estimate of the parameter of interest. We can do this, and this is what I call the subspace method. And I show you how this works in practice in just a second. But let me here point out something that is actually the issue with this method. That's why it's not maximum likelihood, but it's suboptimal. By this replacement of model parameters with data, we actually put noise implicitly into the regressor matrix, and it makes the least squares estimator suboptimal. What we need instead is a lot more difficult procedure that corrects for the noise in the regressor, but this requires nonlinear optimization, and it's not feasible to do in real time for the application I have in mind. So before I go to the numerical experiments to show the performance of the method, let me say that so far I kept it simple, but this is just a short explanation that things can be complicated in a very many interesting directions. One of them is if we measure not from one sensor, but from multiple sensors, we can do what is called data fusion and take into account different properties of different sensors, different accuracy, different speed, and that will be all taken care of in an optimal way by the method I showed. We can derive confidence bounds, which is very useful when we do estimation with noise, so that we can also forecast, predict not only the point estimator, but also its uncertainty. And finally, we can generalize this to time-varying parameter measurements by simple replacement of the weighted least squares problem with exponentially weighted least squares, which discounts past data. So in the simulations that I present, one method I compare is the model-based, assuming I know the exact parameters of the data generating system. So this is the maximum likelihood, this is the best you can get. And the method which is the data-driven, it doesn't use the true model, it uses only the data, and of course you not get as good performance as the maximum likelihood estimator, but the question is how far is from the optimal, and how would you compare it with the naive estimator, which is just using the noisy data and basically wait for the transient. The performance criterion that I show is measuring the difference between the true parameter and the estimated parameter in certain norm over a number of Monte Carlo repetitions. So if I do the simulation, you can see the red line is the optimal ML estimator, the blue dashed line is the data-driven method, and it's improving a lot from the dotted line, which is the direct measurements by not doing any processing. Here is an experiment with change of parameters. So first I have true value of the parameter 1, and it switches to 2 after 25 seconds. You can see again that the red line, which is the error of the common filter, the ML estimator, is very small over the first period, but it's very large over the second period. Why is this? Because the parameter, the common filter is tuned for the parameter 1, and when you get the switch, the common filter is not anymore correct. However, with the exponential weighting, the data-driven method recovers back to small error because it adapts by using only current data. This is a prototype for proof of concept, which is extremely simple that you can do with equipment of not more than a few hundred euros. It's the Lego Mindstorm setup of DSP with a temperature sensor. And by doing some real-time experiment, you can see again that although not as spectacular as in simulations, you can do improvement with the data-driven method. And the common filter here does not give in a steady state as a good estimate because, of course, the model in this case is not exactly linear time invariant. So this thing can be even valorized in equipment, and the simplest possible setup of first-order dynamics is already useful, as I show here in this commercial product of temperature using proprietary predictive technology. That's not my method, it's somebody else's method, but it's the idea of doing cheap DSP processing for speed up of measurement device. So to wrap it up, for the application, dynamic measurement is basically steady state value prediction, and you can do it for high order systems, so it need not be simple first or second order as the examples I showed. It can be arbitrarily complicated system. You can do not only fast measurement, but also accurate measurement due to the property of the estimator to be maximum likelihood. And online computation, which is, if you want to do it optimal, is still an open question how to do the ML estimation in real time, but you can do the subspace method suboptimally in real time. Future work, as I said, numerical efficiency in ML estimation. Real-time uncertainty quantification. I said you can predict the uncertainty, but we do only this. This we can do only offline because of computational complexity of the prediction, and how to do it in real time is still work in progress. And finally, generalizations to more complicated process than LTI, like nonlinear and even multidimensional. And to just advertise again this framework of structured whole rank approximation, I advertise you to invite you to look at the web page with some publications, software, and this has connections to different application areas as shown in the figure. So thank you for your attention.
Thank you very much, Ivan. It was a very nice presentation. We have some time for comments, questions, or discussion. Does anybody else wants to ask something?
Oh, I don't want to just take all the time, but thank you indeed, Ivan, because that's what's very elucidating about the type of work and applications you do. I believe it's plenty of things to explore to have a good collaboration. Just to focus a little bit in if I understood correctly, when you mention a model, like for instance this the simplest one, the model for the evolution of the temperature, I assume that you put this in, I think it was in slide 15. You put this small a, which is a scalar quantity, right? Which is practically what we would in our field we would replace by, I don't know if it's the matrix of conductivities or the inverse of the matrix of conductivities in continuum mechanics when we discretize it with any discretization method. So if I understand correctly, in the type of problems that we do, the parameters are the coefficients that allow us to compute this matrix, but this is somehow hidden in this coefficient A that you use, right?
Mm-hmm. Yeah. Yes. So here it's a simple first-order model. The parameter is a scalar, but indeed, if you have a distributed model where the y is itself maybe vectorization of some process distributed over time, and on top of this, this is a function of time, so it's a spatial-temporal process. Then things can be extremely complex. Then the parameter becomes maybe more general than a matrix. It can be a tensor.
Yeah, of course.
And this makes it indeed very hard to estimate these parameters because they are of high dimension and you need a lot of data to estimate them. Still, if you do the direct method of bypassing the model, there's no free lunch. You would be somehow also relying on approximation of this complicated process, but you avoid the need to work with the huge amount of data to estimate the original process of high dimension. So there is hidden somewhere approximation in direct path, which direct path, I didn't have time to elaborate on this, requires some trade-off between complexity and accuracy. This is the hard question of how you choose the hyperparameter n in the finite dimensional LTI case, or it can be more complicated question of choosing regularization parameters if you solve distributed problem and you regularize and you need to tune these regularization parameters.
Okay, thank you. Thank you very much.
Thank you, Ivan. Does anybody else want to ask something? Any comment? Otherwise, let's close
I may ask another one, because
of course.
Sorry to capitalize everything, but you talk a lot about confidence bounds, and I assume that you are including in that the possible error, also probably in the possible uncertainty, the possible error coming from data. That's right. My question would be, do you have any possibility of including the error coming from the model itself? Or do you have thought, or is there any, because that's part of the thing we do also, to try to balance the error coming from data and model, and have kind of assessment of the error in the inverse problem that comes from both sources.
Yeah, it's a very good question again. That if we work with the given model, and that's the equation here on the top, then we have exact knowledge of the matrix on the left and noisy y. So assuming the noise is zero mean white Gaussian, we have standard regression problem. We have the standard results for the uncertainty of the parameters. That's the easy case. If we, as you suggested, have non-exact parameters of the model, this means that the O matrix in this regressor matrix is itself, let's say, noisy or perturbed. Then it's a difficult question in general to predict how this noise or uncertainty in the model parameters affects the estimates. It depends. Why it's difficult? It's difficult because it enters in a very structured way in the regressor matrix. The O matrix, to remind you, is this matrix which involves parameters C and A, but A is powered. It goes to 0, first, second, and so on powers. It's multiplied by C. So if you have the standard setup of stochastic uncertainty, even if this uncertainty is Gaussian, because of the nonlinear transformation of the parameters, this Gaussianity will not be satisfied anymore. And what will be the effect of this non-Gaussian disturbance on the estimate of the parameters U and X for which you solve? I mean, you need to do some approximation, first, second order approximation, and predict. I mean, there's some perturbation analysis, but to answer this question, but I haven't seen any specific result for what you're asking. What I considered is the problem with the data, where again you have basically the same issue, that now the perturbation comes not from CA, but it comes from the data itself, from Y. And it enters the regressor matrix in a slightly more feasible way to analyze, because it's not nonlinear transformation, but it's linear transformation. The Hankel matrix is linear with respect to the Y. Well, here you have the Van der Monde matrix, which is nonlinear. In this case, we did analysis, and even for this linear perturbation in the regressor matrix, this is called, by the way, the errors in variables regression problem, the results are not as good as I hoped, because you get some formulas, but these formulas are dependent on the true parameter values, which you don't know, and computation is not something that you can easily do in real time, which is the goal for dynamic measurements. So to wrap it up, it's again a very long answer to a short question. It is a genuine problem how to analyze uncertainty in this setup. You can do it quick and dirty, but the actual correct solution of finding the estimates of the uncertainty of the estimates, and moreover computing efficiently this uncertainty and computing it in real time is an open problem.
Thank you again, Ivan.
Yeah.
Thank you again, Ivan and Pedro. Is there any other question? If there are no more questions, then this time let's close the session now. Thank you again, Ivan, for the presentation. It was very nice. And see you all in the next session of the Simna Seminar course, which is next week.
Pleasure. Thank you for inviting me.
Thank you. Bye-bye.
Bye.
Thank you. Bye.